Estrella is a group of 15 students working on the analysis of magical phenomena that happens when a giant Jupiter-like planet falls in love with its host star and gets a little too close to it. A spoiler, they form bond. I'd like to invite Team Estrella to present their presentation.
Yeah, so good evening to all. I'm Rohan Thomas Matthew and I'm representing Team Estrella. We are here to present our findings of the internship under the subtopic of stellar physics. Yeah, so we would like to convey our sincere thanks to our mentor, Mr. Sundar sir, and our coordinators, Rutuja and Priyanka. We would also like to convey a thanks to Nikita and Sujay for providing us the opportunity to do the internship under SSERD. We would also like to thank Pavan for all the interactive, informative sessions throughout the internship period. And also a special mention to AF Lanza for helping us during the internship with the theory. Yeah. So our team members are listed in the slide. Our team leader is Vasant Kashyap and our assistant team leader is Abha Vishwakarma. So here we go. So the problem statement for our team is the analysis of stellar chromospheric activity enhancement due to close by hot Jupiters with elliptical orbits. So what do you mean by stellar chromospheric activity? Stellar chromospheric activity is the result of the magnetic interaction between the hot Jupiters and the host star. So what happens is, due to this interaction, due to this magnetic interaction, specific regions of the host star will become hotter and brighter. And such specific regions where this phenomena can be found are called as chromospheric hotspots. So also one more term we used here is hot Jupiters. By hot Jupiters, what we mean are exoplanets which have a similar mass to that of Jupiter's, and they are having a very high temperature. So why this approach of studying the stellar chromospheric activity? To study such phenomena and determining the magnetic field using the old conventional method is very difficult. So by using this approach of studying the stellar chromospheric activity, it becomes very easier to determine the magnetic field and also to some extent understand the phenomena of the magnetic interaction of the magnetic field of the host star and the hot Jupiter. So in our presentation, we'll be giving an introduction to certain terminologies used. And then in the literature review, we'll be discussing about certain models, previous existing models. And in the methodology, we will be discussing about our approach using an elliptical orbital system and drawing a comparison with the previous existing models. In the results, we'll be discussing about certain important findings, what we have extracted from the internship period. And then this is then followed by a conclusion and we'll be taking up a few questions. So now I hand over to Advait with the introduction.
Yeah, so when these giant heavy mass bodies come very close to their parent star, they form some hotspots on their parent host star because of the magnetic field interactions between them. As the mass of this planet is much heavier and it comes so close to its parent star that it forms a circular orbit. After studying the observations read by A.F. Lanza, we found that the observation period of the stellar flux emission is the same as the period of the planet. That means the period of our hotspot, period of the planet, is periodic. Then the second most significant observation which was made after studying is that the period of the star and the planetary period or the orbital period of the planet were in synchronous, which you can see in this animation. So what do we mean is that the hotspot is rotating at the same angular velocity as that of the planet. Now my friends, you can see over here, I have a question for you. Why is that the center of the star, the hotspot and the planet not in a straight line? Yeah, so the answer for the same is a phase lag, which means that the maximum flux of the stellar emission will be directed towards the observer only when the planet is at a theta degree with respect to the hotspot. And as we can see over here, the that our planet and our hotspot are much periodic in their motion. Now I would like to ask my internmate Ava to continue further.
Yeah. So now let me give you a few seconds to absorb this meme over here, and I hope you can understand this. So going to continuing to the literature review, we read about three primary models which have been used to describe chromospheric activity due to hot Jupiters. The earlier model among these is by McIver and team, who used the misalignment of the stellar rotation and the stellar magnetic dipole axis to explain the observed phase lags of the chromospheric emission. But they weren't able to explain the any phase lag greater than 90 degrees. So we decided to continue our literature survey, and we landed on the paper by Prius and team, who used Alfvén waves, which are a special kind of magnetohydrodynamic waves, which were used to explain these phase lags. But it turns out that this approach was a little too complicated for our team to work upon, and also the no energy considerations were made in this paper. So we decided to move on and study the Lanza model, and we decided to select the Lanza model simply because it accounts for many of the systems that are there, and it considers a very simple magnetohydrostatic model for the coronal field to explain the phase lag observed in these chromospheric hotspots. And it was also within the scope of the team. So now that we have chosen this model, let me give you a brief review of the AF Lanza model. The AF Lanza model considers a core assumption, which is that the magnetic field of the star is axis symmetric. Now, given this axis symmetric magnetic field, Lanza took the magnetic field configuration from the paper by Newkirch, and also took a flux function by the paper by Flyer and team. And using these two, he was able to calculate the equation for the phase lag. Now, let me explain this equation for a minute. The phi of q term over here in the left-hand side is the azimuthal angle of the field line when it is near the planet. And the phi of q naught term is the azimuthal angle when that same field line is near the stellar surface. So this difference phi of q minus phi of q naught will give me my phase lag. And in the right hand side, we see that it is a definite integral. The lower limit of this definite integral is a constant, which is dependent on the stellar radius, and the upper limit of this constant is dependent on the distance of the planet from the star. So given a circular radius, the upper limit is going to stay constant. So so the phase lag that we would get from this equation would be a constant. So now I would like to hand over to Vasant, who will explain how we modified this equation to account for elliptical orbits.
Regarding elliptical orbits, the first thing that we have to consider is the dependency of the planet through time. So the planet's distance from the star would depend as a function of time given where exactly the planet is. It could be very close, it can be very far. So we ran through all the previous results that Newkirch and Lanza have taken into account, and we found that the integrand, that is under root gq prime, that function, whatever is inside the integral, will not change depending on the distance of the planet. So it is a very general function for any given r, but what changes is the upper limit of this integration, that is q. So this upper limit q depends as mod alpha times r minus a, where a is a constant and alpha is the helicity parameter. Both of these are determined by the system, but the small r depends on the planet's distance from the star. Because for an elliptical orbit, this would vary. We have taken an ellipse whose r determined, this r vector would vary as a function of theta parametrically. So for an elliptical orbit case, we were not able to solve this integral analytically, so we turned to computer models for solving it numerically for us. So for every given value of theta, we found out one particular value of phi, that is the phase difference or the phase lag, and we computed this throughout the interval 0 to 2 pi to give us how the integral will change for every given value of distance of the planet from the star. Now, I would like to call Ayusha to explain about our results.
Okay, so now I'll tell you about the results that we have obtained. So Lanza did his calculations by considering the HD 179949 star planet system, where the eccentricity of the orbit of the planet is 0.014, which means that the orbit he considered is almost circular. So the first graph that we have here has the normalized phase gap between the chromospheric hotspot and the planet in the y-axis, and theta, which is in radians, in the x-axis. So from the observations that have been done so far of the phase lags, it is clear that for large orbital radius of the planet, there is a greater magnitude of phase lag. And hence we expected that when theta is equal to 0, that is when the planet is farthest away from the star, we'll have a bigger magnitude of phase lag between the hotspot and the planet. And when theta is equal to pi, the phase lag will reduce because it means that the planet is closer to the star. And we found these observations to be consistent with our plot. So the next thing that we have done is that we have varied some of the constant parameters and observed the changes in the plot. So first of all, we increased the eccentricity from 0.014 to 0.1. That is, we are now considering a more elliptical orbit. We see that the nature of the graph remains the same, but the variation in the magnitude of the phase gap increases from what it was in the previous case. So the next graph here has Lanza considered the semi-major axis in case of HD 179949 as 9.67 times the radius of Sun. If we increase the value of the semi-major axis to 10 times the radius of the Sun, which means that now there is an increased distance between the star and the planet, we again see increased magnitudes of phase lag. So in the next graph, we see the variation of phase lag with theta in case of reduced theta naught. So theta naught is a constant used in the integration formula. There in the denominator, we have a term GQE, where GQE is equal to sine square theta naught. So Lanza considered theta naught to be 38.85 degrees in his model. Now we reduce theta naught to 20 degrees and we can see that the magnitudes of the phase lag have decreased than that we obtained in case of 38.85 degrees. Also, Lanza considered the stellar radius to be 1.2 times the radius of Sun. So if we decrease the stellar radius to 1.1 times the radius of Sun, then the limits of integration changes because both the upper limit and the lower limit includes the stellar radius in their equation. So the phase lag decreases, and since the limits of integration have changed, the entire range of variation of magnitude of phase lag decreases. And lastly, in this graph, if we increase alpha, which is the helicity parameter, from minus 0.19 to minus 0.1, we see a decrease in the magnitude of phase lag for same values of theta. Now I pass on to Devrupa for the conclusion and discussion part.
So as a conclusion, I would like to emphasize on the basic results that we have obtained from our work. So firstly, our model was a more accurate model because here we have taken the work of Eric Lanza and extended it to the elliptical orbits. Here, the phase lag between the host star and its planet is calculated as an integral over the function GQ. This function GQ is can be extended as a linear combination of the Bessel functions. Here, the GQ has a 0 at the limit R equals to RL. So that can very well explain the phenomenon of on and off mechanism in the chromospheric activity. Now, what is this mechanism? The mechanism is if in our model, the magnetic field is dependent on the GQ. So it's very well understandable that the entire magnetic field is confined to between the stellar surface and the upper limit R equals to RL. So when an planet is moving in the elliptical orbit, as long as it is within this limit range, there will be a magnetic reconnection between the star and the planet, and the chromospheric activity could be observed. But when the planet reaches beyond R equals to RL, the magnetic interaction will lost, and the chromospheric activity will cease. Later in the equations, as we can see that from the equations, it is quite understandable that with the increase in the position, the phase lag also varies, and with and this observation was quite consistent with the graphs we have got, and this also verified the flux function. And for the discussion part, for the discussion part, I will like to talk about the synchronicity and the stellar orbital rotation. So what we did is in our work, the orbital plane and the equatorial plane was in the same angle, was at the same angle. There was no misalignment between them. Actually, the synchronicity and the alignment is actually the misalignment synchronicity is achieved to the time interaction between the star and the planet. But in our work, we have only dealt with the magnetic interaction and not taken tidal interaction into account. So we haven't dealt with the asynchronicity also. Lastly, I will like to say that there are many exoplanet systems which has elliptical orbits, and three of them are listed here. And for instance, Kepler 420 AB has an eccentricity of equals to 0.83. So the atmospheric activity has been observed in these planets, but there is no such models that fits in this observation. So our work can be extended to such a systems as a future work, or as in future we can work with it. Also, we can work on systems for which the equatorial plane is not aligned with the orbital plane. So I would like to conclude here and will ask Vasant to carry on further.
So this internship has been an amazing experience for the whole team. And here are a few things that we consider to be our best moments. And the first one is like the bingo that was organized in the second week as the fun event. And we went bonkers over this, and we tried to fill every possible box. And we were not able to collect enough newspaper reports to make a collage because nobody was so future conscious. And in the further weeks, we had Abha making a parody of Love Me Like You Do, which turned out pretty amazing. We had no instrument and it was her vocals only, and everybody loved it. Every day, like every time after the meeting, we usually would play Pictionary or draw something on the whiteboard. And turns out we have pretty good artists in our team. I think we would like to end this internship with a positive note of working further into this particular topic with the help of everybody else in the team. And
Good work, guys. Really good work. Really enjoyed your presentation. Thank you so much.